Inside almost every modern machine, electricity is quietly being converted into controlled mechanical motion. An electric motor performs one astonishing transformation. Invisible current becomes force, torque, and useful movement. No single inventor created the modern motor. Generations of experiments solved different parts of the machine. Volta's battery gave researchers something static electricity could not provide: a sustained and controllable current. In 1820, Ørsted showed that electric current creates a magnetic field capable of moving a compass. Reversing the current also reversed the magnetic field, revealing a controllable relationship between electricity and magnetism. Ampere and other researchers showed that magnetic fields exert forces on wires carrying electrical current. The crucial challenge was turning a momentary sideways push into continuous rotation around a shaft. The following year, Michael Faraday demonstrated continuous electromagnetic rotation with an extremely simple apparatus. Faraday's device proved the principle, although it could not yet deliver practical industrial power. The first motor produced elegant motion, but its torque and construction were unsuitable for useful machinery. Coiling wire around iron concentrated the magnetic field and created a much stronger, controllable magnet. Sturgeon's electromagnet turned electric current into a switchable magnetic force, far stronger than a bare wire. Electromagnets introduced a new possibility: machines whose own motion could repeatedly switch electrical connections. A rotating coil would stop after half a turn, unless the current changed direction at precisely the right moment. The split-ring commutator reversed current automatically, allowing magnetic torque to continue in the same rotation. Electrical polarity changed every half turn, yet the shaft kept rotating because the torque direction stayed consistent. These interacting parts created the basic architecture of a practical direct current motor. Thomas Davenport adapted electromagnets and switching contacts into machines intended to perform real mechanical work. Davenport demonstrated an electric model railway, proving that motors could propel vehicles rather than merely laboratory devices. In 1837, Davenport received an early American patent specifically covering an electromagnetic motor. His motor could drive a printing press, but expensive batteries made continuous operation economically impractical. Early motors improved faster than their power supplies, leaving inventors trapped by weak and costly batteries. Moritz von Jacobi built a more powerful motor by arranging several electromagnets to produce repeated head torque. Jacobi's experimental boat carried passengers, demonstrating electric propulsion at a scale far beyond tabletop models. The boat worked technically, yet its batteries consumed too much material for practical transportation. Faraday also discovered induction, showing that changing magnetic fields could generate electrical current from mechanical motion. A generator and motor are closely related machines, converting energy in opposite directions through electromagnetic interaction. Ring armatures help distributed electromagnetic action around the rotor, instead of concentrating it in one coil. More coils reduce dead spots and produce steadier current, torque, and mechanical performance. Graham's machine made efficient, continuous current generation practical, and soon demonstrated reversible motor operation, sending electricity from one machine into another, revealed a powerful route for transmitting mechanical work. Electricity could carry power farther and more flexibly than belts, ropes, or rotating factory shafts. By the late 19th century, the recognizable direct current motor contained nearly every essential modern component. Brushes transferred current into the spinning rotor, but friction and arcing gradually wore the contact surfaces. Direct current motors offered excellent control, although brushes demanded inspection, cleaning, and periodic replacement. Varying voltage or current allowed operators to control speed and torque with remarkable precision. Reliable direct current motors helped electric streetcars replace animal power across rapidly expanding urban networks. Frank Sprague combined motors, controls, and power distribution into practical systems for urban electric transportation. Electric motors made elevators faster and more controllable, helping cities grow vertically instead of only outward. Early factories distributed power mechanically from one central engine through shafts, pulleys, and dangerous belts. Individual motors allowed each machine to start, stop, and operate independently wherever production required. Electric drives transformed factory layouts by separating machine placement from the geometry of mechanical power transmission. Motors supplied motion on demand, reducing the need to keep an entire mechanical system continuously turning. Strong starting torque made direct current motors valuable for traction, hoists, and other demanding loads. Rail vehicles required powerful acceleration, smooth speed control, and reliable operation under constantly changing loads. Although DC motors worked locally, electrical systems still faced difficult questions about generation and transmission. Alternating current could be transformed efficiently, making long-distance power distribution far more practical. A single alternating field changes strength and direction, but it does not automatically create continuous rotation. Offset alternating currents can combine into a magnetic field that turns without any moving electrical contacts. Galileo Ferraris independently demonstrated rotating magnetic fields and explored motors driven by alternating currents. A changing stator field induced rotor-rotor current through magnetism, eliminating direct electrical connections to the moving part. Interaction between induced current and the rotating field generated torque, without a commutator or carbon brushes. Nikola Tesla developed a polyphase system, built around the same powerful idea of rotating magnetism. Tesla's 1888 patents described motors, generators, and distribution methods for a coordinated alternating current system. Westinghouse acquired Tesla's patents and worked to turn polyphase concepts into commercial electrical infrastructure. Polyphase alternating current linked efficient transmission with motors that could operate far from generating stations. Three-phase currents produced a smoother rotating field and more consistent torque than simpler arrangements. The cage rotor used conductive bars and end rings, creating a rugged closed circuit with no brushes. Dolivo Dobrowolski built a successful three-phase cage motor that strongly shaped later industrial designs. An induction rotor must lag behind the magnetic field, so changing flux continues to induce current. This speed difference, called slip, maintains induction and allows the motor to produce useful torque. When load increases, the rotor slows slightly and automatically develops more electromagnetic torque. Removing commutators and brushes made induction motors durable, inexpensive, and well-suited to industrial service. Three-phase induction motors became workhorses for pumps, fans, compressors, and production machinery. Single-phase motors required additional starting methods because one alternating field alone could not choose a direction. A capacitor shifted current timing, giving many household motors stronger and more reliable starting torque. Shaded pole motors traded efficiency for extreme simplicity in small fans and low-power appliances. Universal motors operated from alternating or direct current and delivered high speed from compact packages. Compact high-speed motors placed substantial mechanical power inside portable tools and domestic appliances. Synchronous motors rotate at a speed fixed by supply frequency and the number of magnetic poles. Large synchronous motors offered constant speed and could also help manage electrical power factor conditions. Feedback transformed motors from simple spinning machines into precise controlled actuators. Servo systems continuously compare commanded motion with measured position, correcting errors almost instantly. Modern robots rely on multiple coordinated motors to convert digital instructions into accurate physical movement. Brushless motors moved current switching from wearing mechanical contacts into solid-state electronic controllers. Electronic commutation improved efficiency, reliability, speed range, and precise control of torque. Variable frequency drives let standard induction motors operate efficiently across changing speeds and loads. Speed control can save substantial energy when pumps and fans rarely need maximum output.
Motor efficiency depends on reducing electrical resistance, magnetic losses, friction, airflow drag, and control loss.
Improved winding design lowers resistance and reduces heat produced while carrying the same current. Thin insulated laminations restrict unwanted circulating currents and reduce energy lost inside the magnetic core. Special electrical steels reduce hysteresis losses as magnetic fields reverse thousands of times each minute. Efficient bearings, accurate alignment, and balanced rotors preserve energy while extending machine life. Optimizing only the motor can miss larger losses hidden in the equipment and process it drives. Motor-driven systems consume a major share of industrial electricity because they move fluids, air, and materials. Electric motors quietly sustain urban water pressure, drainage, and treatment every hour of the day. Fans and compressors use motors to control temperature, ventilation, and refrigeration across modern buildings. Motor-driven refrigeration protects food and medicine from factories to stores and homes. Modern electric trains combine robust motors with electronic control for efficient, high-torque transportation. Electric vehicles use motors that deliver strong torque immediately, while remaining efficient across a wide speed range. Immediate motor torque simplifies acceleration and can reduce the need for complex mechanical transmissions.
During regenerative braking, the traction motor becomes a generator and recovers part of the vehicle's kinetic energy.
Electromagnetic machines can exchange electrical and mechanical energy in either direction when their operating conditions change. Permanent magnets can increase power density and efficiency. They supply rotor magnetism without continuous electrical excitation. High-performance magnets introduce material costs, environmental concerns, and geopolitical supply dependencies. Induction motors avoid permanent magnets and remain attractive where robustness, cost, and supply flexibility matter. Reluctance motors produce torque as magnetic structures seek the lowest dist resistance path through the machine. Modern performance depends increasingly on sensors, power electronics, and software, rather than mechanical design alone. Advanced control lets hundreds of motors coordinate complex production with speed, repeatability, and microscopic accuracy.
Reliable miniature motors position scanners, meter medicines, and assist delicate medical procedures.
Spacecraft use electric motors to point instruments precisely without constantly firing thrusters. Fast electronic control allows multiple motors to stabilize drones through continuous tiny thrust corrections. Electric motors have become so compact and reliable that their presence often goes unnoticed. A single electromagnetic idea now animates billions of machines across nearly every part of civilization. This machine emerged through accumulated discoveries, competing designs, and decades of engineering refinement. Every motor still relies on magnetic fields exerting controlled forces that create rotational torque. Engineers develop different architectures for switching fields, delivering current, and controlling the moving rotor. No motor is universally best. Design choices depend on performance, control, maintenance, cost, and materials. Small efficiency gains matter enormously. Similar motors operate continuously across entire economies. The largest savings often come from matching motors, controls, and driven equipment to actual demand. Condition monitoring can detect developing faults early. reducing energy waste, downtime, and future motors must balance efficiency with repairability, material recovery, and long operating life. Recovering copper, steel, and magnets can reduce mining demand and preserve valuable engineered materials. New materials improve density and efficiency, while the underlying electromagnetic principles remain recognizably familiar. Axial flux designs can package high torque into short machines suited to specialized transport applications. Electric aviation depends on efficient, lightweight motors, but energy storage remains a larger constraint for long flights. Decarbonization and automation are expanding the number, power, and intelligence of electric motor systems. A fragile wire circling a magnet began a technological chain that eventually moved the modern world. Civilization's invisible engine turns controlled magnetism into useful motion almost everywhere.
Antarctica looks like a blank white edge of the world.
But beneath that ice is one of the least familiar landscapes on Earth.
In some places, the ice is so thick it completely buries mountains, valleys, lakes, and rivers.
What seems like a frozen surface is actually a lid covering an entire hidden continent. This is not just frozen weather. It is a continental-scale archive hiding a world underneath. Scientists have spent decades trying to answer a deceptively simple question. What is down there? Under Antarctica are mountain ranges, deep basins, liquid lakes, active water networks, and even volcanoes. To see them, scientists had to learn how to look through ice without directly seeing through it. So this hidden world was mapped indirectly, using signals, reflections, gravity, and motion. Aircrafts crossed the continent with radar instruments, turning empty white space into measurable structure. Radar works because radio waves can travel through the ice and bounce back from what lies below. That reflection turns hidden terrain into a profile, almost like an ultrasound of a continent. Some of Antarctica's mountains do not pierce the surface at all. The ice hides relief so large that, without radar, the landscape below would remain almost impossible to imagine. That is the first key to Antarctica. The surface tells only part of the story.
Below the ice, Antarctica is not uniform. East Antarctica and West Antarctica are built very differently.
When the bed slopes inland beneath grounded ice, retreat can become dangerously self-reinforcing. And Antarctica contains enormous buried basins, some so vast they shape how the entire ice sheet behaves. Beneath the ice, low areas collect pressure, heat, sediment, and sometimes liquid water. That leads to one of Antarctica's strangest secrets: lakes that never see the sky. Scientists have discovered hundreds of subglacial lakes beneath the Antarctic ice sheet. These lakes stay liquid because pressure, insulation, and heat from below work together.
The ice above acts like a giant insulating blanket, while geothermal heat and pressure help prevent complete freezing.
The most famous of these is Lake Vostok, buried beneath nearly 4 kilometers of ice.
Lake Vostok is not a puddle. It is a vast body of water hidden from the atmosphere for possibly millions of years.
That isolation makes it scientifically irresistible, because it may preserve ancient chemistry, sediments, and clues about extreme environments.
Subglacial lakes matter not just because they exist, but because they sit inside a dynamic system of ice, rock, water, and sediment. Some hidden lakes are isolated for long periods. Others connect to moving water networks below the ice. In other words, Antarctica hides not just lakes, but plumbing. Water can collect, shift, drain, and refill, sometimes changing how the overlying ice moves. That matters because water at the base can reduce friction and alter the speed of ice flow. Some of Antarctica's ice does not move evenly. It funnels into ice streams, where hidden conditions below help control the pace. Many of these fast-moving route deep troughs and basins carved into the buried continent. And then there are the mountains, some of the most dramatic features of the Antarctic ice. Deep within East Antarctica lies the Gamburtsev subglacial mountains, a range entirely buried beneath the ice sheet. Their peaks and valleys are large enough to resemble a major alpine system, yet almost nothing of them is visible at the surface. So under the ice is not just scenery, it is geologic history locked under extreme cold. These buried mountains matter because they influence how the ice above forms, thickens, and flows. In fact, some scientists think the hidden landscape helped organize the very birth of the East Antarctic ice sheet. Because the bed beneath parts of West Antarctica slopes downward inland, retreat can expose thicker ice to further retreat. This is why the hidden shape of Antarctica matters globally. The bed below helps determine how ice loss can accelerate. The buried landscape channels ice like river valleys channel water. Some of the world's most closely watched glaciers depend on subglacial terrain that is largely invisible to the eye. When researchers worry about instability, they are often really worrying about geometry hidden below the ice. And water is not the only thing under Antarctica. Heat matters too. The hidden base of the ice sheet is thermally uneven, with some regions receiving more geothermal energy than others. Where basal heat is higher, more melting can occur at the bottom of the ice. Yes, beneath parts of Antarctica are volcanic regions, some ancient, some potentially still active. That heat may come partly from deep crustal conditions, and in some places, from volcanic systems. So the underside of Antarctica is not a single frozen floor. It is a patchwork of dry zones, wet beds, soft sediments, and heat anomalies. In some regions, the ice does not rest directly on hard rock. It rests on soft sediment. Topography, water, heat, and sediment all interact to decide how the ice sheet behaves. At this point, Antarctica starts to look less like a frozen wilderness and more like a layered machine.
But none of this hidden world would be visible without a toolkit built for indirect detection.
Radar is the backbone of subglacial mapping because it can reveal the buried shape of the bed over long distances. Gravity measurements add another clue by showing where mass is distributed differently below the ice. That helps researchers infer buried basins, crustal blocks, and structures hidden far below the surface. Magnetic data can reveal tectonic history and hidden geological provinces beneath the ice. Seismic studies add depth, showing how the crust and mantle beneath Antarctica are built. Taken together, these methods reveal that the hidden continent below the ice is geologically varied and surprisingly complex. Satellites contribute another essential piece. They track the surface shape and movement of the ice itself.
Sometimes the surface even rises and falls in response to hidden lakes filling and draining underneath.
The hidden Antarctica we know today is really a stitched-together picture built from many partial methods.
And that stitched picture has transformed Antarctica from a blank white mystery into a mapped but still partly unknown buried continent. A century ago, much of this would have been speculation. Today, the hidden contours of Antarctica can be drawn in remarkable detail. But mapped does not mean finished. Antarctica still contains gaps, uncertainties, and unresolved questions. One of the biggest questions is biological. Could life persist in some of these isolated subglacial environments?
The conditions are harsh, dark, cold, isolated, and under pressure. But microbial ecosystems may still be possible.
That possibility matters beyond Antarctica, because similar hidden water environments may exist on icy moons elsewhere in the solar system. In that sense, Antarctica is not just a remote continent. It is also a natural laboratory for extreme hidden worlds.
Sediments beneath the ice may also record how Antarctica changed long before the modern ice sheet formed.
Because Antarctica was not always the frozen world we know now. Its buried geology and sediments contain clues to that transition, from greener past conditions to the growth of a massive ice sheet. That past matters because it can help scientists understand how the Antarctic ice sheet responds to long-term climate change.
And in the present, the hidden world under the ice directly shapes the future of glaciers, coastlines, and sea level. The reason this matters so much is simple. Antarctica stores enough ice to transform coastlines if large parts become unstable.
But that instability is controlled not just by air temperature or ocean heat. It is controlled by what the ice is resting on. A buried ridge can help stabilize a glacier. A deep inward basin can make retreat harder to stop. This means Antarctica is not one single risk. Different hidden landscapes create different outcomes.
The map below the ice tells scientists where fast pathways exist from the continent's interior to the sea.
Exploring this hidden world directly is difficult, expensive, and scientifically delicate. That is why so much of Antarctica's hidden world is still understood remotely, through increasingly refined observations. Researchers observe what they can, infer what they cannot see directly, and use models to test how the buried system behaves. Better maps of the hidden bed improve predictions of how ice may move in the future. In a place where the bed is invisible, uncertainty begins below the ice. But so does progress. The more Antarctica is mapped, the less it looks like a simple ice cap, and the more it looks like a buried continent with active internal systems.
At its core, the mystery under Antarctica comes down to three things: landscape, water, and heat.
Landscape shapes the flow. Water changes friction. Heat alters the base. Together they control the ice sheet from below. A hidden landscape in the far south helps influence a planetary system that affects everyone. So what is hiding beneath Antarctica? Not one secret, but an entire buried world. It is a world of hidden relief, trapped water, deep history, and physical forces still shaping the ice above. And despite everything we have learned, some of its most important details are still being discovered. That may be the most Antarctic fact of all. Even the most mapped hidden continent on Earth is still partly unknown.
Once you know what is underneath, the blank white surface never looks blank again.
Antarctica is a continent buried by ice, but defined by what the ice conceals. Under the ice is a landscape that helps explain Antarctica's past, its present, and part of our future. Because what is hiding beneath Antarctica is not just buried geography, it is a system that still matters to the world above it.
This means Antarctica is not one single risk. Different hidden landscapes create different outcomes.
The map below the ice tells scientists where fast pathways exist from the continent's interior to the sea. Exploring this hidden world directly is difficult, expensive, and scientifically delicate. If a buried lake has been isolated for immense spans of time, scientists must avoid polluting the system they hope to study. That is why so much of Antarctica's hidden world is still understood remotely, through increasingly refined observations. Better maps of the hidden bed improve predictions of how ice may move in the future. In a place where the bed is invisible, uncertainty begins below the ice. But so does progress.
The more Antarctica is mapped, the less it looks like a simple ice cap, and the more it looks like a buried continent with active internal systems.
At its core, the mystery under Antarctica comes down to three things: landscape, water, and heat.
Landscape shapes the flow. Water changes friction. Heat alters the base. Together, they control the ice sheet from below.
That means the story under the center of Antarctica can reach all the way to the edge and out into the ocean. A hidden landscape in the far south helps influence a planetary system that affects everyone. So what is hiding beneath Antarctica? Not one secret, but an entire buried world. It is a world of hidden relief, trapped water, deep history, and physical forces still shaping the ice above. And despite everything we have learned, some of its most important details are still being discovered. That may be the most Antarctic fact of all. Even the most mapped hidden continent on Earth is still partly unknown. Once you know what is underneath, the blank white surface never looks blank again. That may be the most Antarctic fact of all. Even the most mapped hidden continent on Earth is still partly unknown. Once you know what is underneath, the blank white surface never looks blank again. Antarctica is a continent buried by ice, but defined by what the ice conceals. Under the ice is a landscape that helps explain Antarctica's past, its present, and part of our future. And that is why one of Earth's coldest places remains one of its most important scientific frontiers. Because what is hiding beneath Antarctica is not just buried geography. It is a system that still matters to the world above it. Beneath every ocean, continent, and city, Earth may be storing an astonishing amount of water hundreds of kilometers underground. But this is not a liquid ocean in a cavern. The water is chemically locked inside solid minerals. At these depths, water exists mainly as hydrogen bound into crystal structures, not as free-flowing lakes or seas.
The most important zone lies roughly 410 to 660 kilometers below the surface.
Geologists call it the mantle transition zone, a pressure-built layer between the upper and lower mantle. This hidden reservoir matters because Earth's surface ocean and deep interior are part of one extremely slow water cycle. Water can travel downward with sinking tectonic plates, disappear into minerals, and return through melting and volcanoes. The difficulty is obvious. No drill can reach anywhere close to the transition zone. So scientists investigate this water indirectly, using seismic waves, laboratory pressure experiments, and rare minerals carried upward from depth. Then one tiny diamond inclusion provided the first direct sample from this hidden reservoir. To understand that discovery, first strip Earth into the layers pressure creates beneath our feet. The shallow upper mantle is dominated by olivine, a mineral with relatively limited capacity to store water. As pressure rises with depth, the same chemical ingredients rearrange into denser crystal structures. Near 410 kilometers, olivine transforms into wadsleyite, a mineral that can hold far more water. Wadsleyite does not contain underground droplets. It stores hydrogen inside defects in its crystal lattice. Deeper still, wadsleyite changes into ringwoodite, another high-pressure mineral with major water storage capacity. At about 660 kilometers, ringwoodite breaks down into minerals that generally hold much less water. That sharp drop in storage capacity can force water out and help create tiny amounts of melt. The transition zone may therefore act like a deep sponge, and, at its boundaries, like a water trap. But a mineral's capacity to store water does not prove the entire global layer is filled to that capacity. Because the transition zone is unreachable, scientists read its properties through the way seismic waves travel. Abrupt mineral changes at 410 and 660 kilometers create seismic discontinuities that geophysicists can detect. Seismic tomography converts thousands of travel times into images of faster, slower, colder, and hotter mantle. Their depth, sharpness, and local variations reveal temperature, composition, and possibly the presence of water or melt. Some low-velocity layers near the transition zone boundaries are consistent with small amounts of partial melt. Laboratories test that interpretation by recreating deep earth pressures and temperatures in diamond anvil cells. When hydrous ringwoodite transforms under lower mantle conditions, experiments can produce melt between the new mineral grains.
Seismic observations beneath North America found velocity drops where mantle flow models also predicted downward movement across 660 kilometers.
Together, experiments and seismic data support dehydration melting as one way water may remain trapped near the transition zone. Still, seismic signals and experiments were indirect. Scientists needed a piece of the deep mantle itself. The crucial sample came from a rough diamond recovered near Juína, Brazil. Deep source eruptions had carried the diamond upward fast enough to preserve a mineral formed hundreds of kilometers below. Inside the diamond was a microscopic inclusion, too small to see without specialized instruments. X-ray diffraction identified the inclusion as ringwoodite, the mineral expected in the lower part of the transition zone. It was the first reported terrestrial occurrence of this high-pressure olivine polymine polymorph in a natural sample. Infrared spectroscopy showed that the inclusion was water-rich, in the mineralogical sense. It contained substantial hydroxyl. The preserved inclusion indicated roughly 1% water, locally, within the transition zone mineral. That was direct evidence that at least part of the transition zone is hydrous, not proof that the whole layer is equally wet. The diamond solved one question and sharpened another. How representative was that tiny piece of deep earth? A speck inside a diamond had transformed the debate from pure theory into direct observation. The discovery was widely described as an ocean in ocean inside Earth. But that phrase can be deeply misleading. The mineral stores water as hydroxyl, hydrogen bonded within the crystal, not liquid water filling open space. Hydrogen can substitute into defects where metal ions would otherwise occupy the structure. Each grain stores only a small fraction by mass, but the transition zone contains an enormous volume of rock. Across a planetary shell, even 1% water would represent a quantity comparable to vast surface reservoirs. Experiments show wadsleyite and ringwoodite can hold several percent water by weight under suitable conditions. If the entire zone were near saturation, its capacity could equal several surface oceans, but that is a hypothetical upper limit. The real mantle is almost certainly uneven. Wetter near some subduction systems, drier beneath other regions. Where tectonic plates carry hydrated rock deep into the mantle, local transition zone water may become concentrated. Temperature, iron content, mineral chemistry, and mantle flow all change how much water these crystals can hold. Water changes electrical conductivity, seismic speed, strength, and the way mantle rock deforms. Even when hidden inside crystals, hydrogen can make mantle minerals easier to deform over geologic time. That means deep water can influence mantle convection and the long-term movement of tectonic plates. The deep cycle begins when surface water reacts with oceanic crust and becomes stored in hydrated minerals. Sediments, altered crust, and hydrated mantle rocks can transport water toward a subduction zone. As the plate sinks, rising heat and pressure destabilize many water-bearing minerals. Much of that water escapes at shallower depths, helping generate magma beneath volcanic arcs. Volcanoes return part of the subducted water to the surface through magma and gas. But not all water returns immediately. Some hydrated material survives and continues much deeper. Inside the transition zone, wadsleyite and ringwoodite provide new crystal structures capable of storing that hydrogen. The result may be localized reservoirs shaped by ancient slabs, mantle circulation, and mineral reactions. When hydrated material crosses a boundary into minerals with lower storage capacity, water must move somewhere else. Some enters melt, some may migrate upward, and some can be recycled back into the transition zone. This is the deep water cycle, a circulation measured not in days, but in millions of years. Its pace is almost unimaginable, yet over Earth history, it can move enormous quantities between surface and interior. At the base of the transition zone, ringwoodite transforms into bridgemanite and ferropericlase. Because these minerals hold less water, the transformation can trigger dehydration melting. A 2014 study combined high-pressure experiments, seismic imaging, and mantle flow models to test this process. The observed pattern was consistent with partial melt forming where hydrated transition zone material moved downward. Even a very small melt fraction can strongly reduce seismic velocities and change how the boundary appears. If melt rises back upward, dehydration melting could help keep water concentrated inside the transition zone. Together, melting at both boundaries may create a long-lived geochemical filter around the deep reservoir. A similar release may occur when hydrated wadsleyite rises above 410 kilometers into shallower olivine stability. This does not prove a continuous global ocean. It describes mineral-bound water, possible melt, and a highly variable mantle. Every estimate of deep water depends on combining evidence that sees the mantle in a different way. Electrical conductivity can increase when hydrogen is present, but temperature, melt, and composition can produce similar signals. Seismic data also require interpretation. Slow waves may indicate water, melt, documentaries, high temperature, or chemical differences. The mantle is heterogeneous, so one region cannot automatically represent the entire planet. The diamond is direct evidence, but it is still one tiny sample from one locality. Even the diamond's source history depends on models of deep eruption, mantle flow, and mineral preservation. As a result, published estimates of the transition zone's total water content still span a wide range. New deep diamonds, better experiments, and denser seismic networks can gradually narrow that uncertainty. Future maps may reveal whether deep water forms broad reservoirs, narrow slab-fed zones, or a constantly shifting patchwork. The answer will probably be dynamic, because mantle water moves with a planet that never stops convecting. Water weakens mantle minerals, changes viscosity, and can redirect how heat and material circulate. That links deep water to plate tectonics, mantle mixing, and the generation of magma. Water helps rock melt at lower temperatures, making it a powerful ingredient in magma production. Volcanic degassing returns deep water to the atmosphere, where it can eventually rejoin rivers and oceans. Surface water then enters new crust, rides tectonic plates, and begins the journey downward again. The surface ocean is visible and fast-moving. The deep reservoir is hidden and geologically slow. Over billions of years, Grevenst exchange between them may help shape the long-term stability of Earth's water budget. Earth's oceans did not evolve separately from the mantle. The planet's interior has always been part of their history. A planet's mineralogy and deep water cycle may help determine whether water stays at the surface, enters the interior, or escapes. For Earth, the transition zone may be a bottleneck that stores water and controls how easily it crosses into deeper layers. Its mineral phase turns pressure boundaries into valves in the deep water cycle. The story is not an underground sea. It is a planet-sized chemical circulation through solid rock. Its central reservoir lies in the mantle transition zone, between 410 and 660 kilometers deep. Wadsleyite and ringwoodite can store hydrogen in crystal defects at concentrations far above shallow mantle olivine. A diamond from Brazil provided direct proof that at least one part of this zone held substantial water. But one local sample cannot tell us how wet the entire transition zone is. Scientists therefore combine diamonds, seismic waves, conductivity, experiments, and models to estimate the hidden inventory. The minerals may have capacity for several ocean equivalents, while the actual amount remains uncertain and uneven. What is certain is the cycle. Water moves down, changes minerals, and melting, and eventually returns toward the surface.
Even chemically bound water can influence the mechanics of the planet above it.
So the phrase "ocean inside Earth" is useful only if we remember what it really means. One reservoir flows in waves. The other is stored atom by atom inside rock. The next discoveries will come from smaller samples, better instruments, and clearer images of a world we cannot visit. The biggest question remains simple. How much water is actually moving through Earth's hidden mineral reservoir? The answer will reshape how we understand oceans, volcanoes, plate tectonics, and the long-term evolution of the planet. Earth is not hiding a sea beneath our feet. It is hiding water inside the architecture of the planet itself. That line connects rain, oceans, sinking plates, deep minerals, magma, and volcanoes across geological time. The familiar water cycle runs through clouds and rivers. The deeper cycle runs through rocks and tectonic plates. Deep storage can last far longer than any surface reservoir, even though the mantle itself keeps moving. Every journey through the mantle changes the mineral-to-mineral container and therefore changes where the hydrogen can go. That is why pressure, not empty space, creates Earth's hidden water reservoir. The reservoir is invisible because the rock still looks like rock. The water exists in the chemistry. A microscopic inclusion revealed a process operating across a layer thousands of kilometers wide. We know the mantle can hold oceans of water. We still do not know exactly how much it holds today. What lies beneath our feet is not a secret ocean. It is a hidden planetary cycle written into minerals. And that hidden reservoir may be one reason Earth has remained a water world for billions of years. Around 1200 BC, the Eastern Mediterranean was one of the most connected places on Earth. Kingdoms traded copper, tin, grain, timber, oil, textiles, and luxury goods across hundreds of miles. Bronze made the system possible, but bronze needed both copper and tin was often the harder ingredient to obtain. Palaces did not just rule. They stored food, organized labor, tracked goods, and held entire economies together. Information was part of the infrastructure too. Scribes recorded shipments, taxes, rations, and diplomatic messages. This was an international system where rulers wrote to one another, exchanged gifts, and depended on long-distance stability. It was a world of diplomacy and competition, where peace, trade, and prestige were tightly linked. And that made the entire system powerful, but also dangerously interdependent. Then, within only a few generations, many of these kingdoms and palace centers collapsed or changed beyond recognition. The mystery is not that one city fell. It is that so much of this connected world began failing at once. To understand the collapse, you first have to understand how much everyday life depended on fragile chains of movement and control. A single shipment could carry the metal that armed armies, repaired tools, and signaled wealth across an entire kingdom. Maritime trade was the bloodstream of the Late Bronze Age, especially in the Aegean and Eastern Mediterranean. The chain reaction risk. Food mattered just as much as metal. Palace systems had to collect, store, and redistribute grain to keep labor and authority intact. One major suspect in the collapse is climate stress, especially drought and the harvest failures that can follow it. Paleoclimate evidence suggests parts of the region experienced periods of aridity around the time the system came under pressure. Less rain can mean weaker harvests, tighter rations, higher prices, migration pressure, and political instability. And when food becomes uncertain, the letters from this period start sounding anxious, urgent, and sometimes desperate. One of the clearest windows into the collapse comes from Ugarit, a wealthy port city on the Syrian coast. Ugarit sat at a strategic crossroads, tied into trade networks that connected empires, islands, and coastal states. Its surviving tablets preserve something rare: the written voice of a system under sudden strain. Some letters mention enemy ships, missing support, and threats arriving too fast for help to organize. This is where the famous Sea Peoples enter the story, though they remain one of the most debated parts of the collapse. Ancient Egyptian records describe groups attacking by land and sea, but they do not solve who every attacker was or why they were moving. They may have included displaced groups, mercenaries, migrants, raiders, or peoples pushed by the same wider stresses hitting everyone else. The deeper problem may have been convergence, several shocks arriving in a system already stretched thin. When one major node in a highly connected network fails, the damage does not stay local.